Today we're going to talk about performance tips for Julia, and you should look at the manual within Julia. There's a good section, has a lot of good tips here, worth a read. We're going to hit many of them, but definitely worth reading in more detail. The first thing I want to say about performance is that this is probably the last or one of the last things that you should do. Many reasons for that. One is that your code is going to change, right? So sometimes we write a function and we just want to make it really great, but as we go on, that function, as we continue to develop our package and our codes, that little sub function is going to change. Another reason is that we really want to have good unit tests, and so we kind of wait until the most important thing is to get your code correct, right, first. And so that's where we have these good unit tests. We can make sure everything is functioning correctly, and then we can start thinking about performance. And if we have that good set of tests, then when we're doing performance testing, we're almost always changing the code around. And this is one form of refactoring, right? So anytime we're doing refactoring, that's a common place to introduce bugs. So we want to have those tests so we can refactor, performance test, and then run our unit test again and hopefully, see that we didn't break anything, or at least not break anything that we're testing. And then, another reason is that, as we'll see, we really want to be driven by data. It's very easy to think we know what's going to help improve our code speed, but we're often wrong, right? And so we can waste a lot of time trying to speed something up by just guessing, oh yeah, I've got too many allocations here, or yeah, this is, not the best method here. And sometimes it is faster, but those things are in the noise and it makes no real difference. Or it's not even faster. And so really we want to be driven by the data and test, profile, and see where we should make our improvements. That said, it's still helpful to be aware of some of these tips beforehand, just so we can try to avoid some things as we're writing code. So the first example, I'm going to go through 3 examples. First one, very simple. And this actually from ChatGPT. I tried to get a bunch of examples, and I didn't like most of them. There were like things I didn't use very often, like strings and whatever, but this one's okay. It's very simple, but what I'm trying to do is create an array of integers here, and I want the array to be, 1, 2, 3, 4, 5, and so on, right? So we're just creating an empty array, pushing things onto it, returning the result. So let's call this function with a million entries, so it's somewhat interesting. And if I want to see how long it takes to run, there's a macro I can use that's built in Julia called time. We'll see why, as I've written, is not the best way, but let's just run this. And here we go. Okay, and it printed out the array, which I didn't really want to see. So I'm going to put a semicolon to suppress the output. That was suppress. By default, it's going to print whatever's at the very last of my script, and I didn't want to see that. But time gave me some measure of the time and some measure of the allocations, close to 1 million as we expect. So there are a few reasons why I don't want to just run time. This example doesn't really highlight it because it's so simple. But if I hover over time here, I can see the doc string. And one of the things is, actually, I'll just say first, when I call a function the first time, you may recall that the first time I run it, or if I've changed things, and now it's the first time since I've changed things, it's got to compile or recompile that function. So my timing is going to be a mix of compilation time and runtime, which is probably not what I want. I just want the runtime. So a good practice is to just to be sure that it's fully compiled. Let's just run it. We're going to do it some timing. Call it, and then let's call time. But since 1.8, as it says here, and I'm in 1.9 here, it's kind of tried to give some indication of that. It says recompilation time being shown separately from compilation time was introduced in 1.8. So here's an example. It just creates this random matrix 10 by 10, and it's just timing multiplying 2 matrices. And like, well, that took quite a bit of time, but then you look over here and it's trying to give you a hint like, well, actually 99.9% of that time was just compilation time. So if you do it again, you see, oh yeah, okay, super, super fast. So yeah, this is just one way to avoid that. But even still, let's just run this a bunch of times. Okay, so let's look at my timings, and you can see there are kind of quite a bit of variability. Not too surprising, right? On a computer, I'm going to get some variability. Those things are running on my system, and depending what's in my memory and registers and all that. But what I really want to do is run it a bunch of times and get some statistics, like look at perhaps the median time. Good way to do that is this package called benchmarktools, and to use it, all I have to do is replace time with btime. And if I do that, I don't need to call it beforehand, because what btime is going to do is it's going to call this function many times. I believe 10,000 times. Well, I should say it's 10,000 times with a limiter as well. So if like your function already takes multiple seconds, it's not going to do that 10,000 times. So it's 10,000 times or less within some time limit. Look at the documentation for more details. So if you go to benchmark tools, you can see some information here about what it does. But let me just run this real quick. Notice this is taking quite a bit longer because it's running it 10,000 times, and then it's going to give me a median time here, which is going to be a better representation of how long this actually takes. Because again, there's a lot of variability. So 10 milliseconds, 10.2 milliseconds. So, some of these were, actually most of these were, probably all these are a little bit slower, but this is a much more accurate representation. And there are other macros that it comes with, like benchmarks. I can get a distribution if I want. I can look at the means, mins and maxes, and so on. And there are other things here, so take a look, but probably btime is what I use most often. Sometimes the benchmark macro, really useful when you want to compare things. But when we're doing rough comparisons, time can be nice. Still use it, as we'll see today, just because I can do things fast and I can iterate and I can see big changes. But when things are kind of in the noise, probably I don't care. But if I want to resolve them, and especially if I want to put things in a paper, I'm going to run btime, right? So let's improve this function. If you haven't thought about it already, you should think about that now. What's kind of the issue here? And this one's a little bit obvious, kind of issue in all languages, right? That I really want to pre-allocate. I'm basically, allocating new memory every time as I keep making this array bigger and bigger and bigger. So let's just make it once. Let's make a vector of type some integer type. I'm going to use 64-bit integers. I don't care what's stored in it initially because I'm going to rewrite everything. So just whatever's in memory at the moment. That's of size n. And now I can just assign elements as I go, and I need to give it a different name here because I'm going to compare both. And I'm just going to use the time macro. And notice I am using, since I've got a size here, I need to use 10 to the 6. This is just, I can't use 1 e to the 6, by the way, because that's a float. So I'm going to use 10 to the 6 to keep that an integer size. And I want to suppress that last thing. So yeah, even with time, right? Again, there's some variability, but I can see multiple orders of magnitude, so that's not in the noise. This is massive improvements, and allocations went from 1 million to 2, right? And again, if I wanted to refine the time, I'll use btime, but these differences are so stark, I'm not going to worry about it here. Okay, let's go to a second example. This one comes from actually the Julia documentation. I'm going to jump back to in a sec, but it's a common thing, so I just want to highlight it here. So I've got a function. It's very, very similar to the last one. Only difference is instead of storing things in this big array, we're going to add them together. So we're just going to sum. So there's nothing to pre-allocate in this case because we're only just storing one float and just adding it along as we go. So let's time this thing. And let's try and do what we said we probably should do. Although again, this is so small, compilation time will be negligible. And there it is. And so this code is not very fast. And why is that? Well, I'm going to introduce another macro called code warn type, which is maybe not the easiest name to remember. But what it does is it helps us look for type instabilities. So I'm going to call it on my function. And let's just run this one line and see what happens. This output takes a little bit to digest, to get used to, I should say. But the main thing I'm just going to highlight here is these reds. If I see red, that's not good. That means I've got code that's type unstable. So remember what Julia does is that unlike in C or Fortran where I need to indicate everything is, well, see, it's kind of tried to give me a hint here that this is a float. I haven't had to do that I could have done that kind of thing, right? I could annotate everything and everything that comes in, things that come out, and type everything. But Julia is going to be able to infer things for me, which makes things really nice and agile. So kind of like Python and MATLAB in that way in terms of the agility, but but can get the performance of these compiled codes because the compiler can figure out types and then make things really efficient. What it's telling me in this case is it can't do that. It's saying, I have no idea what these types are. Like it's saying S could be any type, I could be any type, body, which means what's being returned out of this function, which is some loop. So S is saying, yeah, that's what you return is anything. I have no idea. So I can't really compile anything here. It's just going to be interpreted. It's just going to be like as if it was a regular Python, not a NumPy Python, but a pure Python or a MATLAB code that's going to be interpreted. So what can I do? Well, or why is that happening? The problem here is that X is a global variable. And like most languages, we want to avoid, really any language, we generally want to avoid these global variables, not just for performance, but they're bad for, often bad for just logic because it can be changed anywhere, right? So it can be really hard to introduce bugs. So one way we can fix this is just put everything in a function. We just call this the main function. Oops. Let's call this the main function and indent this thing over. And I'm just going to now call main and time main. Just time that thing instead. You know what? Before I do that, actually, let's get a more proper time. I'm going to use B time. Just so we can get a better indication of what this is before I compare things, in case it's not too different. I don't want it to be in the noise that we're trying to compare. And, again, that's going to take a minute. Oh, there we go. So I'm going to start changing it while that's going. So I'm just going to copy and paste this. I often I'll do this when I'm performance testing if I want to compare. Sometimes I'll copy the functions, as we'll see later, but here I'm just going to do some changes in place. So I'm going to save where I was. So I want to see if I'm making improvements relative to that. So now I'm going to call my main function. Let's move X inside. So now X is not a global variable. And let's run it. And it's again B time, so it's running it 10,000 times. While that's going, I'm going to uncomment this. So I'm going to want to check my type stability again. So yeah, way fewer allocations. Went from 90 milliseconds to 600 microseconds. So what is that? I think 2 orders of magnitude roughly improvement. So yeah, big deal. Let's run code warn type here and notice no reds. It knows X is a vector of float, so it's going to compile that efficiently for that. And by the way, I could have created a vector of integers or whatever I wanted, and it could do that too. But yeah, so rand is floats, and so it's able to figure that out. I can compile it for different types of water. In fact, this code I think is a little weird. I'm just pulling an example. I think we normally would have written it like this. I would have had a function, and then I could do this. I could have a main function and do this, but sometimes it's a little annoying. I'm just in the REPL. So what you can also do if you don't want to just throw things in a function there, if you're using B time, is that we can use I think they call it interpolation. But we interpolate this variable X. Basically, it treats it no longer as a global here. So it's like it's blocked it off here. So if I do this, this will be fast. It's a little, notice I'm not actually going to be comparing to exactly what I did before, because before I was comparing the time of creating X and summing, and now I'm just creating the summing part. But anyway, I'm just showing this as an example, right? So it's around the same order, but no allocations here because I pulled the X out of that. But it's a nice way at the REPL when I've got some things maybe in my script here, and I want to make sure I'm not using global variables here. So BTime is going to ask you to use that $ syntax here, and you can again go read about here on benchmarktools. I just wanted to go back to the performance tips here and highlight. We've hit some of these top ones already, right? Performance critical code should be in a function. So scripting is great for prototyping, getting going, testing things, and so on. But put them in functions, get them in packages, get them in modules. Avoid these global variables. Sometimes you really want them, and there's ways you can get around it here, right? Like you can put const, you can define types and things, but generally, you don't really want those. Sometimes you do. We've talked about time, right? And time can give you these things. It can also give you allocations. And here it's showing that example where, look, this is all compilation time. Run it again, so you get a good timing, right? So we've hit some of these first few things. And then tools, profiling. So we've talked about We haven't talked about that. We're going to talk about that in a second, but we've talked about this code warn type. We've talked about time. We're going to talk about this profile view here in a second. So let's get to a third example. This is an example. This morning, I just asked some of my students, send me, if you got something that's would be a good performance example, like something that's slower than you want it to be. Maybe I can see if we can do this for a demo. So one of my students sent me this code. This is not the code that he sent me. I've simplified it massively. So this is just extracting the essence of one of the parts of one of the functions of the code, just as an example. So in his code, he's got a function that's going to create a matrix. And in the matrix, there's a size here, and there's this thing called normals. These are surface normals. So this is some geometry, and it's discretized. And in each discretized segment, there's a vector that points out that's normal to that geometry. So it's giving me some indication of surface normals all over the place. So this is a matrix of normal vectors, and the other dimension is, all the different panels or discretized pieces. And so he initializes a matrix, and this is, I'm keeping kind of the same logic or, essence of it. There's a double for loop in there. And so he's pulling out one of the normals, and then you calculate some velocity. And this is definitely not the formula. There's more complicated, but the essence is that it involves the geometry at one part I influencing some other part J. So there's some influence there. I just multiplied things, but that's not what happens. And then we take some dot product of its velocity and a normal. So we're getting the normal component of velocity. Again, not really important, but this is, again, kind of the essence of it. And then in some main function, I created these normals randomly because, they'd be computed based on some geometry, but I just created some random data here. I wanted to set a seed just so that everything is the same numbers every time. Probably shouldn't matter for performance, but, it doesn't hurt. I set the size as 200, so I've got 200 discretized segments here. And then why I'm iterating here is for normal workflow for this is that there'd be an optimization. And so we'd create this matrix. There'd be a bunch more things that would happen. In this case, is an aerodynamics code. So it'd calculate, maybe some from these influences, calculate some lift, drag, or whatever. We'd have some objective and constraints. And then the geometry could change by the optimizer. So I'm just perturbing these normals here. And this has got to be a dot equals because this is a matrix. And this is a float, so I got to broadcast that across. And I do that a bunch of times, and 100 is small, but I didn't want to wait. So there it is. Very simplified version, but some of the essence of the things that were there. So let's time this, and I'm going to do that. I'm not going to use B time here, maybe at the end, again, because I don't want to wait. And I'm looking for bigger changes here. So let's run this, and yeah, I need to plot random, and yeah, dot, I need to plot dot. So I need to grab those. All right, there we go. So it took, roughly 0.2 seconds, 8 million allocations. All right, so I'm gonna change this a bunch of times. Instead of changing in place like the last example, I'm going to just keep copying and pasting them so we can see a progression here. I'm gonna do many of them. I'm gonna put this _1, so it'll be easy for me to change that from 1 to 2 and so on. And I don't want to interfere with the other ones that are there. Oops. So let's do that. So let's create a version 2. And in version 2, I'm just gonna kind of go off what I see here. And maybe what I would see first is I might say, well, look, we just did an example of pre-allocation. And here I'm creating this vector, this matrix A, kind of a big matrix, 200 by 200, and I create that every iteration. So why don't I just create it once and pass it in? Maybe that will save me some time. So I'm going to cut that, pass it in as an argument, and now it's just going to be modified in place here. So I could initialize it outside of this loop, pass it in, and if I was doing the normal kind of Julia convention, this of course is not any function, it's just agreed upon convention. I would put an exclamation point, which means that one of these arguments is being changed in place. It's not just all being passed in. But I'm not going to do that because I'm just going to do a bunch of examples. I want to keep it simple here and my find or replace. Okay, so I'm going to do that, and hopefully that is fine. So let's do that. So now I've got 2 timings, and I mean, maybe it was slightly faster, maybe not. I mean, it's certainly in the noise. So I didn't think to really do anything. So remember what we said, we really don't want to just yes, we want to kind of be driven by the data here. So one thing we could do, if we go back to those documentation that says, oh, profiling is a good thing to do. Julia has this built in. It's got a profile function here, it's got a macro, and it's going to spit things out we can look at. There's also other packages like profileview. It can take that and make some figures and things that maybe are a little easier to read. What I like to use is built into Julia, or sorry, into VS Code. In the Julia extension of VS Code, there's this macro here called profview, and it makes a nice kind of visual, and also does some highlighting on the syntax or on the code itself, which is helpful, as we'll see. So I find this helpful. So let's use that. Let's actually just look at the main one first. And I'm going to run it first just in case. I don't think anything's changed, but same kind of thing. We don't want to be profiling compilation time. Okay, so it takes a minute to unpack this. And the colors mean different things, which I've forgotten. But the thing I want to point out right here, we can look at the docs later, but is the size of these bars gives me some indication of the time, right? It's going to tell me, so in other words, here's root. It always starts at root. So all these things that have the same length, I'm going deeper and deeper in the code. Each function is calling the next function, or is calling the next thing. But notice how they're all the same. So like there's nothing happening, right? No time is being lost. So basically you can see from here to here, I went to main, main one, nothing really changed, although there is something here with this one. It's taking some time here, create matrix. And so eval, I can see the biggest split here is in create matrix. So my main function, create matrix, is most of that block, which is not surprising. I also notice if I look at main one, see this bar here, it's an indication of time. And if I hover over it, it says 79% of the samples. That's a rough indication of the time spent in this function. Almost all of it was in this function, which is not surprising. And if I go back to create matrix, right? So if I went into create matrix, I can see, well, about half the time is in this branch, half is in here. So what is it doing? It says it's trying to get an index, it's copying some data over, and it's saying, well, this line here is a big one, 59%, 9% here. And the one that I tried to, get rid of, it said, well, it was like basically 0%, one sample, like, so yeah, I made it faster, but it was so incremental, it did nothing for me. So again, that's just an example. We want to look at the data here. So let's now just go to 2, because that's the one we want to start improving from. So the view didn't really change, basically the same. So what's the problem here? Well, I should probably rerun it. Maybe my line numbers are off. Yeah, they are, because I added something. Okay, so there we go. Just reran everything because I got my line numbers off. So yeah, get index is taking a lot of time. Copying is taking a lot of time. This line here seems to be taking a lot of time. So I might say, well, okay, one thing that's happening here is I'm indexing into this matrix. So let me go look at the performance tips. And over here, it talks about indexing into array, and it says, consider using views for slices. So in Julia, if you slice an array like this, right, which is very common, we're going to create a copy of that data. The exception is when it's on the left-hand side. So like here, I'm not copying AIG, I'm assigning something into it. So I wouldn't copy it, I'm viewing it, putting it in there. But if it's on the right-hand side, I'm taking that, in this case, this row, and I'm copying it over, and I'm doing some operations on it, multiplying it, and so on. So let's keep reading here. If you're doing many operations on that slice, then maybe that's what you want to do, right? That may be good because it's more efficient to work with that contiguous copy instead of having to refer back to it. But if we're just doing a few simple operations, then that allocation and copying is going to give us a performance hit. So alternative is to create a view. And it talks about view and views, and you can go look at these. So, but I'm just going to show you how you would use this, for example. So in this case, I could do view, give it the name of the array, and then just use my normal indexing syntax. That's one option. It looks a little bit clunky. So there's also another macro, or another option, which is this macro view. And I don't know, I think I might have to put it at the front of the line. I'm not sure, but what I normally would use actually is just views here. That's gonna be a little bit easier. I have one view, I could use views. I'm trying to see if I can see if view has to be at the front. No, maybe not. I don't know. Probably not. Okay, so I think it was fine as it was. But here, views, it's going to put a view for everything in the block. So within this for loop, it's going to do it for here and for here. That's all I've got, but that's just a nice thing. And sorry, I want to keep creating new examples, so I'm going to make version 3 here. So let's do my copy and change stuff here, and my face is in the way. 3. Okay, so now I can change it. Let's make some views and see if that improves things. So we're looking at the timings over here. Again, the first two, nothing really happened. But as I looked at kind of the data here, now I've made some improvement. I've reduced my allocations by half, and my timing is yeah, decent. So what is that? That's like, I don't know, 30% faster. So great. Okay, we're making some progress. Now my thing has changed here. We still got this dot product has got something, but create matrix here. There's a bit of copying going on. So actually the next thing I'm going to do, let me just copy this again, is I'm going to do what I just said we shouldn't do, which is I'm just going to like guess what to do. I'm going to do this actually because this is, I did a session with my students earlier today, and this is what they suggested next. So we're going to do that, and it hits the performance tips, and it's going to help a little bit. So we're going to do it, but not necessarily obvious right from here. It's probably not the next thing I should do. But let's go to the, oh shoot, Julia, performance tips. Okay. There we go. Accessing arrays in memory order along column. So one thing we want to be aware of is that in different programming languages, data is going to be stored in different ways. So imagine some tensor or n-dimensional array. Let's just think of a matrix because it's simpler. We've got this matrix. It's not going to be stored in data in that way, right? It's going to be stored either as column, like column 1, and then stack column 2 below it, and then column 3, or row 1, and then row 2, and row 3. So there's some contiguous order. And so depending on the way it's stored, right, I could be accessing them directly in order, or I might be jumping over to the next column or the next row or whatever, and that's going to be less efficient. And so Julia stores in column order, same as Fortran, whereas Python is going to store in row order. So we want to make sure the way we're accessing the data is compatible with that. So specifically, it gives us a couple examples here, and we're going to look at both of these. But this first one here, I've got these two cases, and this first one, it's called copy columns, copy rows, and we can see copy columns is faster. And so what is it doing? Well, I've got this matrix and I'm doing a for loop where I'm grabbing, what is that? That's all the rows. So I'm grabbing one column at a time. And that's what I want, right? Because those columns were stored in order. So I want to grab one column at a time. But notice what I'm doing, or what the student's code is doing, he's grabbing one row at a time. So let's actually switch that. So let's go in our main function. And let's make this, instead of n by 3, 3 by n. And then now we change these. And so that's a little better. And then the other thing that's happening here is that, yeah, let's look now at the second example. So now we've got two for loops and they're written here together, but this is a nested for loop like we've got. So we could go columns and then rows, or we could go rows and columns, and we should do the first, as we can see from performance timing. So we want the column to be on the first so that we're now fixed in a column, and as we're incrementing the rows, we're staying within that column. So we want this I index to be on the inside, which is opposite of what I've got. So I'm gonna flip these, and then I've got to move the views up here. And now because NI is not indexed till later, I'll do this and call this NJ, and we'll do that, something like that. I think that is right. So let's now compare that time. Look at the times over here, and that didn't really make a big difference. It is a little better, probably should be, but again, we didn't really look at the data here. So let's try number 5. Okay, number 5. So what is it telling me? Again, create matrix 4 is a big thing. Let's jump in here. And it's showing me this line is a big thing. So why? I'm copying things. Why am I copying things? Well, a couple ways I could address this, right? So what's happening is I've got these NIs and NJs. I took views into these things. So these are just views. But now as I multiply them together, and I'm doing a broadcast multiply across them, I've got to create some new memory here, and I'm storing this into V. And so I've got to recreate a new V, allocate a new V a whole bunch of times, because this is a loop within a loop within a loop. And I guess I should look at 5 now, because I want to change 5. But so within this outer loop here, right? And so that's not great. So let's pre-allocate V. So unlike A, this should make a big difference. I could do it way out here. This is kind of the trade-off, right? Like, do I want to keep passing in things or create another data structure to pass in all my things? Maybe. In this case, so I'm gonna think that I can probably get away with. And of course, I'd want to test this, but I think I'm going to get away with just allocating here. So V is a vector. What's its type? Well, it's a function of these normals and its size. You know what I'm going to do? I'm going to use similar because it's the same size as this column of J, or of normals. So let's just grab the first column here. It's the same type and it's the same size, so that should be great. And then now we can do just a dot equal. So we're not creating a new V every time. That memory is already created. We're just now putting it in there. So this is number 5. So let's try that. Okay, that made a huge difference. So we went from something that didn't do much. We looked at the data, made a difference. We did something that didn't look at the data, it didn't help that much. And then we looked at the data, our profiling had made a big difference. And we're now at, I don't know, order of magnitude already. So that's great. Now a lot of my time is in my dot product here. There's still some copying. Here, this dot product, this is still, yeah, taking a lot of copying and iterating here. So I don't know, what can we do? Well, nothing we could try here. Actually, let me just go back before we do that. The thing we just did was called, what did we just do? Oh yeah, we did, what did we do? I'm getting tired, I guess. Oh yeah, we pre-allocated, of course, yeah. I don't know, there's much to talk about there. Actually, there's a good section here. We've showed this already, but oh yeah, here we go, pre-allocating inputs. Kind of obvious how that can help, but I think they make a good point here, which I've definitely seen, which is, be careful, right? You could take this to extreme, and it does generally make your code uglier, makes it harder to read sometimes. And so, test what makes it worth it. You could pre-allocate everything and have your code have basically 0 allocations, but at some point, it's going to mean passing around all these big data structures, which may or not be great. So, but certainly pre-allocation can be a big thing. All right. So let's try number 6 here. Number 6, what I'm going to try is static arrays. And so static arrays, the reason why I think this is going to be helpful is because, well, let me just show you what it says here. Because I have these fixed sizes. So it says if your application involves many small, less than 100, about, element arrays of fixed sizes, meaning you know the size before you execute, you might want to use static arrays. This allows you to represent the arrays in a way that avoids unnecessary heap allocations, and it can specialize the code by the size, for example, by unrolling vector operations. So for example, when you call things like norm, or we're calling dot product, here, for example, when we do 3v minus w, we're allocating things, right? Because we got to store this intermediate array that's 3v minus w, so we've allocated some memory for that, and then the norm is doing some things internally as well, which are going to be allocating additional arrays. And so static arrays basically kind of unrolls this, like as if you had written these, by hand kind of operations yourself, which you can do too to avoid that, but that's kind of annoying. So let's use static arrays. I find it makes, like I said, you could write that, but it makes your code more verbose. I find it harder to read. So in our case, we know that these are all vectors of size 3. There's a bunch of them, but they're size 3 because this is an R3. These are, this is geometry. These are vectors that are surface normals in 3-dimensional space. So static array seems like a good fit. Let's look at the package here. It shows us a bunch of ways that we can initialize. I've got an array already created. Maybe I don't want to do that, but I'm just going to use that. Well, let's see what I'm going to do. I need to call this number 7 now. Am I really on 7? No, I already changed it to 6. Yeah. So let's use static arrays. What I could do actually is just create my normals as static arrays to begin with. But I'm not going to do that because I don't know. Just because it ends up being the same. I think I did some tests earlier, but well, we can try it here. I'm just going to show both ways. So let's create a static array S vector here. This is going to be an S vector of size 3. And this one is going to be an S vector of size 3. And I think that's all I'm going to do. So then this will be a static vector, and these are both static vectors. So that should be fine. Okay, so let's try that. And V is not defined. Yeah, I can't do a dot equal because static arrays are static. I can't assign into them. All right, so yeah, quite fast. This is actually the fastest yet. 0.001, 9 allocations. I don't think I can do much better than that. So I think we'll call that a day. So again, takeaways. Again, after this, you should go back and do B time, but I'm not going to do that because I don't want you to sit here and wait. But that'd be good if you really want to compare, see the improvement. I'd go to B time, but I can see I've definitely made a dramatic decrease in our allocations here. Look at the performance tips. Be driven by the data. Do profiling. Figure out where you're spending your time. Yeah, I think that's good for today.